I'll get started for the current session. So we were working through our introduction to Bioconductor. We introduced ourselves to Bioconductor. We looked a little bit how we can handle sequence information, that coming from FASTA. And in our last session, we learned about one of our favorite packages, genomic ranges. Okay, and this is the package which allows us to import and export features from bed files, intervals, and then manipulate them within the R Bioconductor framework. What's nice is we started to see the lessons we'd learned in sequences. We can actually use our G ranges then at the end to start to extract the sequence under our features of interest. Okay, so we can start to use these objects together and we can start to see that they're really fantastically interoperable. Okay, so the next thing I wanted to cover is genomic scores. And I say scores here, anything where we have a value we want to assign to a particular base pair, we would consider a score. And here we want to see them in the genomic context. So I think one of the first things we looked at for our data formats was this concept of a wiggle file. A wig, I mean, mostly called wig, but the name stands wiggle. And these just allow you to put for a particular chromosome here in a steps of 5, the score at this particular window. Okay, from here to here, we have a score of 50. From here to here, we have a score of 40. And you can imagine if I then looked at this in a genome browser, I can see my bumps and dips of signal. Perhaps a little bit more friendly in terms of file size is bedgraph, whereas we are kind of doomed to write out a value every 5 bases here. And you can imagine genomes are massive. So writing this out every 5 bases, well, especially when they're the same value, is kind of pointless. So what we can do is create something a little bit more like a bed file, right, with our ranges, chromosome, start, end. But this time we're going to extend it to a bed graph, right? So it's again, going to show us the signal over our region. So here we have chromosome 1, this to this position, we have a score of 1. But what's really useful about this, rather than having to write out blocks of 5 and putting the same score there, we just say chromosome 1 from this position to the end of the chromosome, for instance, we have a score of 0. So already this is going to save us a lot more space in a text file, and actually a lot easier for us, I think, to interpret, really. I mean, this is a pain. Cool. So in many situations, though, we're not going to see, I haven't seen actually a bed graph used for about 10 years, probably, other than the ones I create myself. Wiggle files I never bothered using because they're a real pain to set up, although lots of programs will kick them out. Actually, Bigwig is a really great format. So it not only compresses the data, so all this data here, into a computer-only readable format, but it actually provides an index within that file. So when we looked at things like BAM files, we know we have a .bam and we have a .bai. That's the index, the .bai. All of this is in one file in a Bigwig. And hopefully we saw, what genome was this? MM10. We saw at the end of the last session that we could download our data and we could visualize Bigwigs inside IGV. And it was like instant to load it. If you try and load the equivalent bed graph or wiggle file, you're going to find that your computer will start to get loud and we'll have real problems. It's trying to load the whole thing in memory. Bigwig file allows for random access, just shows you the data in the window you want to look at. Okay, we're going to see some of that in action, this random access later on too. So genomic scores are obviously heavily used in genomics and high throughput sequencing, as they offer a mechanism, a very simple mechanism, just to take your data, whatever defined metric you have generated, and review this over a linear genome. So we're going to generate, you will generate Bigwigs for RNA-seq, ChIP-seq, and ATAC-seq, and any other type of sequencing, anything where we can map it to a linear genome, and there is meaning in that mapping, so we can extract a score, we can turn into a Bigwig, but really anything where there is a score associated to a base pair or a window along the genome, we can extract some metrics. So another really common one is phylogenetic conservation. We have tracks available to us in databases which show, say, for the human genome, how well conserved a particular base pair is or a region is. All this we would consider genomic scores, and we may be able to find in a bigwig file. So in our last session, when we looked at beds, we took some ChIP-seq mix signal from the ENCODE consortium. So I think it was this one, ERRN. And anyone who didn't hang around for the exercises, one of the exercises was to go find this and then go and get a WIG file. And I wanted the signal p-value. So they've obviously translated this into some type of p-value score. And we could have downloaded it here. And hopefully then we could actually load that into things like IGV. Okay, so that was this data. It was MM10 CH12 cell line. It's the same data actually I showed you in the GEO SRA lectures as well, how to go get the raw data. If you haven't downloaded this, I think we're going to use this in this course a bit. So you're going to need to download this link. So I think it was in our last session, we had some peaks. This was in the exercise. We had some peaks which we'd filtered down just to those in the TSS. And then we looked at the signal and we could see that our peak here in the TSS had lots of ChIP-seq signal there, indicating a strong binding event right here for MYC. So in this course, we're going to work, I think, with this bigwig at the end. I'm going to warn people here right now, for Windows, bigwig import and export is not supported. So anytime we're going to import using our track layer, it's going to tell us off. And that's because the original libraries which used bigwigs, they were written by UCSC. They were just not built for Windows. That said, there are solutions. We have an internal solution which we're trying to release. Actually, Wei, who maybe you saw, I mentioned RFASP, he's also an author with me on a package to allow us to do this in Windows. There's also another package, Megadepth, we'll cover that. But for now, that doesn't really allow you to import them into R, it just allows you to produce them. For now, if you're on Windows, you're not really going to be able to work with bigwigs. You can work with RLEs, you just can't export them to file. So for this course, I have filtered down, I produced a bed graph for us, and I produced a bigwig. And what I've done is actually just subset down to a region of interest just to make our life a little easier. I'm going to show you how to do that, how I did that later on as well, how I only got data from a particular region. To do this, to use all the functions we're going to use, they come from the R track layer package, which handles much of the import and exporting of genomic intervals. I said it in last session, this may change. Bioconductor updates, they have now a BioC IO package, which may handle some of this. And we're going to use genomic ranges again, which we use to handle all the bed files, to handle our wiggle files, our bed graphs, this kind of genomic score data. So the first thing we need to do is load the library. We can get our R track layer library, just library R track layer. I think previously we needed to we loaded genomic ranges. I talk a little about this, but I wanted to show an example too. I go to the R track layer website. In Bioconductor, ooh, build error, good for them. Every package has its dependencies, its imports, and it suggests things, other packages which it uses to get its job done. So here we can see that this package here, our track layer, depends on genomic ranges, which means that it's going to import and load genomic ranges for us. So we don't really need to worry about loading genomic ranges. It's not going to do any harm if you just type in library genomic ranges, but you will notice as soon as you've loaded this, you didn't need to load this. Okay. So to read in our bed graph, whereas we had import.bed earlier on, now we have import.bedgraph, and we can read in our bed graph file to our object here. So by default, when we read in these genomic scores, it looks like it is a granges object. Okay, so actually this looks a lot like the original bed graph, right? chromosome start, end, and the score in that region. So maybe it makes sense that we're going to, by default, import it like this. And we can see here from chromosome 1, for this long stretch of region, 72 million bases, we have absolutely no signal. And then we have some signal from this region, and then this region we have some score. This is just a G-ranges with now our additional column of score. One thing which is a bit of a pain about beg graphs and bigwigs, you know, they won the format war, bigwigs, but other formats actually allowed you to take into account strand. Because beg graph has no strand information, it's only got 4 columns, chromosome start, end, score. There is no strand information. So when this was imported, all our strands became star, right? And you can see that here. So just remember, beg graph, bigwig, strand list data. Yep. Most of the data we actually dealing with. So here I'm going to import a beg graph. I tell you, beg graphs aren't compressed. You can compress them in some ways, but they're not an efficient way to store data like this. So what we're really going to do is store this in bigwigs. If you are not using Windows, you can use this import.bigwig function. Again, UCSC, when they wrote these tools to make bigwigs, they didn't think about Windows. There are solutions we will talk about later. But here, if you're on Mac and Linux, you just do import.bigwig and you pass it the path to your file, and it's going to do exactly the same as if it was a beg graph. Gives us back our G-ranges, again, seq names, our ranges, our score, but again, no strand information. So beg graph, strand list, bigwig, even though it's computationally, it's, you know, compressed, it's binary format, they still don't have that information in there. So all bigwig, all beg graphs are going to be strandless. So by default, as I said, all our beg graphs and bigwigs got read in when we did this import. We didn't specify anything else, and it gave them as G-ranges. Right? We recognize these because we were using them in the last session. So that means we can do things like our standard accessors. If I wanted to, I could create another G-ranges here, and then I can use that G-ranges to overlap and just retrieve the ranges from my imported bigwig as G-ranges, which overlapped my new range. Okay, so I can already subset my windows of signal just to include those which overlapped ranges. I can use all these tricks I learned for my G-ranges in the last session. Actually, I think the better way to handle genomic scores, it's not a default, but hopefully we can see why it's useful, is to import it not as a G-ranges, the default, but to specify that we want to import it as something we've kind of seen, which is an RLE list. Okay, so we saw RLE in a few different ways before. Run length encoded, that's what it means. And here we're going to have a list of these run length encoded objects. All right, so to get this and start looking at it, we just do the path to our bigwig, but now we're going to say we want it back as an RLE list. I think then the other option we're not going to see, but it's either a G-ranges or an RLE list. I think a simple list was the other. If we look at the class now, it's no longer G-ranges. It's a simple RLE list from the iRanges package. So what is run length encoding? Let's just remind ourselves. Well, we saw this right at the beginning, right? Run length encoding allowed us to save space in our BAM file. And it's really a very efficient way of storing long stretches of repeated values. Okay, so when we had our cigar string, rather than write out 100 M's, it actually just wrote 100M, which means there were 100 matches, 100 M's. When it wanted to deal with something more complex, it had 28M, so there were 28 matches, 1 deletion, and then 72 matches after that. So already right there in the BAM file, we had some type of run length encoding. We've also seen this run length encoding inside R. So when we started looking at our G-ranges last session, we got back when we had imported it here and we had our G-ranges. If we wanted to look at the seq names, the chromosome names, they came back as a factor RLE. Right? And we had issues then. We had to replace seq levels in order to get new seq names. That was the factor aspect. But what we saw was these were RLE, and we hadn't come across this object. I think it's kind of intuitive though. For the first 891 values in this file were chromosome 1. The next 737 were chromosome 10, and so on and so on and so on. So in this case, it means you can store all these values, all the chromosome names for this file in 21 values, like 21 runs, times by 2, because you have one value for the chromosome, one value for, one value for the chromosome, one value for the length, right? So I can take what is hundreds of values, thousands of values maybe, and just compress it into 21 times by 2, one for the length, one for the chromosome. So we're going to save a lot of space internally for memory, a lot of space which is really potentially just wasted. So we can actually make these RLEs ourselves if we want to do our own memory saving. So to do this, we're going to create an RLE just using this RLE function. Like we create anything, we have an RLE constructor. And we're going to supply to this RLE constructor just a simple numeric vector of numbers, and we're going to ask it to actually encode this as a run length for us. So I'm going to give it deliberately a stretch, 0, 0, 0, 0, 0, 3 ones, and then 5 more zeros. We just do RLE on this, and it gives me back not a factor RLE, but this is now a numeric RLE. Right? It tells us we have 3 runs. So we have 21 runs here. Tells me the total length, right? Total length here. And then it tells me here, I had 5 zeros, 3 ones, 5 zeros. To then construct an RLE list from this, we can just take, build another RLE. We have enough then to make a list. So I will put one as chromosome 1 scores, put one as chromosome 2 scores, and then I can create a list of RLEs, an RLE list, the same way I would create a standard list. Except I'm changing the constructor clearly. So RLE list, I give it a name for my new list element. I give it the actual values, my RLE here. I give another name, chromosome 2, and I give it my score RLE, which I just created here. And now I have my RLE list, right? And every element in there is then a numeric RLE, which I've just put in. Okay, so RLE lists are a little bit of an extension of lists. You know, I could just make a list of my 2 RLEs, right? Lists can contain anything. But as you'll see, creating an RLE list allows us to do just that little bit more operations on this data as a whole. So as we've just been saying, RLE allows us to compress the space. We're going to have huge data sets, so we want to compress as much space and store this efficiently. Bioconductor has RLE and RLE list objects, and that's actually what we created here. These were Bioconductor methods, and they're going to allow us to save space. We can really see this in action when we start to look at things like genomic data, and we read in our bigwig a few here a while ago, but we can start to see the space saved here in our example now. If we just look at the first 2 elements of our RLE list, right, which will be here, chromosome 1 and chromosome 10. We can see that rather than writing out any values for chromosome 10, we actually just have a 1 run, and that is the full length of the chromosome, and we have no scores there at all. I've deliberately subset this bigwig, remember I said at the beginning, to just a particular window. So you have no scores here. Similarly on chromosome 1, where we actually have some data, we have this big gap, all zeros. Then we have 65 of this score, et cetera, et cetera, et cetera, until we get past the region of interest, which I have signal over. And then we have these huge expanse of space where we all have zeros again, right? But it's managed to compress the full genome and some scores into just 21,000 runs. So there are only 21,000 2,100 length values, and again 2,100 values here. Okay, so we managed to compress a ton of space, a ton of information here as we've read them in, as an RLE list. Because it's like a list and it's in the name, you can see this list. We can access this now in the same way as we would regular lists. Right? Nothing more we have to learn. If I wanted to get just the numeric RLE for one particular chromosome, I can do my bigwig, and I can just do either the dollar accessor and give the name of the chromosome, right? So this name here, or I could do the double square brackets and again put in our name, but this time in quotes. Okay, and then we can just get back the numeric RLE. And this numeric RLE, which was in our bigwig, is exactly the same as if we constructed it ourselves. Right? We can see that. Now we have our RLE object. We can start to actually work with it a little bit. We can, thankfully, with some magic in Bioconductor, index this just as we would a normal vector. If I want to extract from my RLE just the first 10 scores, I can do 1 to 10, and it's going to go in and subset my RLE just to the first 10 values. Okay, it's not going to give me the first 10 runs because that would be useless. It's going to look in, and it's going to go within the first 10, which is still somewhere in this block. We had all zeros, and it's just extracting that part. Okay, so behind the scenes, somewhere, we can now take advantage of standard vector indexing. Even though this looks kind of complex, I can just extract the first 10 values of my RLE as I would a normal vector. But it's going to save me a lot of memory and a lot of space to keep it as an RLE. I can also replace values in my RLE. Right? I can do this in a really memory efficient way because of the way it's all built up in Bioconductor. If I want to replace just the first 10, just like standard index, I do my square brackets, 1 to 10, and then I give a new value I want to assign to this, 100. And now I can look at my numeric RLE for the whole chromosome, and I can see it's just replaced these first 10 values with 100. I guess this run got 10 shorter. Yep. And then it was exactly the same. Okay. This is done in a very efficient way. You have potentially a vector of length this, right? So holding all those zeros would have been very memory expensive. Subsetting would have taken a long time. Doing this in RLE is really efficient. If, for whatever reason, you do want to convert this back to an RLE, and it might be that you need to use some method which isn't able to deal with this RLE function, we can just turn it back into a standard numeric vector just by doing as.vector. And I obviously subsetted this before because otherwise we'd have millions of values printing to screen. But then we just get a standard numeric vector. We can do the same if we wanted to, and you can imagine this will be very useful for things like ggplot from our values in our RLE. I can actually turn it into a data frame. I just here give it the first 10 values, and then it gives me position here, and then the value I had at that position. And they were all 10, sorry, 100 because we assigned them there. Okay, so we can use all the standard kind of indexing on RLE lists. And we can do a lot of stuff we would normally do with a vector with an RLE list. But if we want to, we can still turn them into a normal vector or a data frame and operate with them there. This you would definitely need to do for things like ggplot. So like with G-ranges, you know, it wasn't just an object. With it came a special set of functions which allowed us to do some of these operations we just need to do with genomic ranges. Overlaps, finding the clearest, finding the nearest region, kind of pair across bed files, across G-ranges objects. RLE in Bioconductor has similar sets of functions which allow us to do some really cool, neat things with these RLE objects. And these include things like arithmetic, mathematical operations. I can say, give me the values in one RLE stronger than the other, higher than the other. I can add, subtract from these. I can perform some logical operations and comparisons. And I can also extract summary statistics. So, you know, to do this in base R would be slow, but Bioconductor have written the program in C and it's wrapped in R. And it allows us to do a lot of this really fast. So let's say I want to apply 1,000 to every single one of my RLE values. I could just do plus 1000. And then you can see now this propagates across my entire RLE. Every value got another 1000. If I wanted to as well, I can do more complex things. I can do plus 1000 times by 10, and then it will apply it to the runs, and it will do this again in a very memory efficient way. We can also perform some logical operations, and this can be incredibly useful. If I wanted to, say, just find the regions in my runs, across my signal, which were below a certain score, or perhaps above a certain score. I may say they're enriched. If they're below, I may say they're background. I can do that again with logical operations and RLE objects. So I can do this is less than 10, and it will look through the runs, and it will find me runs which are less than this value. And we get a new RLE back, which is now a logical RLE, right? And it's given me, I've got a run of 10 false, all this true, false. Okay, so any real value in base R, we can wrap in an RLE and encode like this to save space. So then you can start to use these in combination, and this is where the real power comes. I've got my bigwig into R. I've decided, look, I want to make it look cleaner. I want to remove everything underneath a certain value, and I will set that to 0 as my baseline. Everything else I think is real signal. So I can do that and just, I'll import it, and then my next operation may be, I will then take my chromosome 1, I will give my logical index of all the values in there which were less than 10, and now I'm going to assign them to 0. And we had, what was less? This was true, this was true, this was true. Now if I look at my RLE, anything above that remained, but now I have set these all to be 0 where it was true. And that would have cleaned up my bigwig in a really simple, memory efficient way. Again, I'm only showing one example here, but you can use these in combinations. You can have windows, this less than 10 and greater than 100 or whatever, less than 10 and greater than 1 or whatever. On top of having functions to allow us to, review arithmetic operations, we also have some set of summary statistics we can apply to our RLEs. Okay, so if I want to get the mean value for this long stretch of numbers, I can just apply mean directly to my RLE object, and it gives me the mean value. I got things like max, I've got the sum, right? So I can do all this in a really memory efficient way straight to my RLE. I wonder if I actually, RLE. Okay. Sorry, I'm just going to pull up a help page at this point. I'm going to share my screen in a slightly different way. So just to get a real idea of what we can do with these RLEs, we can do a question mark RLE like we would for any help, right? So then we can pull up this information here on RLE objects. It comes from this S4 vectors package. This is actually the package below iRanges. Tells you how to construct them yourself, right? You can actually just give the values and the lengths. And if we go down here, it's going to start to tell us what methods we can actually apply. You can see there are a ton of methods, different things we can do to compare them. And then here, if I just click on the RLE utils, it gives me a full description of the arithmetic operations. So I can apply any of these. I can do these comparisons, equals, greater than. I can do logic. I can do operations, and I can do what they say is math here. Right, so somewhere in there. So I can log 10 translate or log translate all my values. Some summary statistics I mentioned, max, min, the range of the values could be useful, and then more complex ones here. And then hopefully at the end, some examples too. So if you really want to know full depth of things you can do, 2 RLE objects, I recommend doing the question mark RLE. We're going to cover a fair deal of them, a fair number of them as we go through this anyway, and the exercises too. So that's how we can operate on this chromosome 1 RLE, and I just want to show somewhere at the beginning, I took our full RLE list, which was a while ago, maybe we never show. So I took my full RLE list and I only took the chromosome 1, and that gave me an RLE object, right? This numeric RLE. But what I imported was an RLE list, and I had an element for every chromosome. Okay, so when I import .bigwig, I imported it as an RLE list, and I actually had a value for every chromosome, and it was going to be a numeric RLE. What's really cool, and why I said that lists aren't quite as good as RLE lists in terms of here, why don't we just put all our RLEs in a normal list? I understand them, they were easy. Just by making an RLE list instead, we can do things like here, when we do +10, it knows we have an RLE list, and it knows that it can go through every element and add 10 to every single one of them. Oh, sorry. Right. So very easy. I don't have to do a for loop for every 1 in lengths of my imported RLE list, go through and add 10 to every numeric RLE one at a time. I can just do +10, and we'll apply it to every element in my RLE list. It starts to become super useful when we do things like these summary statistics, because now if I apply max to my RLE list object, what it's going to do is go and give me the summary of the max on every element within my RLE list. Here, that is every chromosome, right? So I have 1 for every chromosome. I have 1 for every chromosome, and then I can do my max on that RLE list, and it's going to work through it, and it will give me back a vector, named vector here, of the maximum score for every chromosome. If I'd done min, it would give me the min, the sum. But the cool thing is, it is applying it to every element of our RLE list for us. So next thing we're going to cover here is that we can actually, like we showed, you can use G-ranges and BS genome objects to kind of extract parts of sequence. We can actually do the same with G-ranges to extract parts of our RLE list object as well. Right? So we don't need to use just normal indexes. We can actually use a G-ranges as an index. So RLE list contains an entry with scores. So what we're going to do here, first we'll just create a G-ranges. Okay, so my ranges. We'll import the bed file of our MIC CH12 peaks. So this is the example from our exercise yesterday. Gives us MIC peaks. We just want to resize that. Oh, it's summits, so it's only going to be 1 value. We'll resize that to be 50 around the center. And then I'm just going to extract those which overlapped this region. This is the region we have some signal in. And then that gives me a G-ranges here. It's just really a subset of the total peaks. Okay. It has a score. This isn't the score from the bigwig at the moment. This is just the score from the peak caller. Okay, but importantly, we have 1 range here, name score, another range here, name score. So we can now use, we can now simply index our RLE object by our G-ranges by taking our RLE list here and doing our square brackets as if we were going to extract it from a normal vector, except rather than providing regions like 1 to 1:10, and it would give us the first 10 values, we're actually going to give it our G-ranges, and it's going to extract the coverage, the score over these G-ranges in separate elements. Okay? So this first element here is length 50. That's because our G-ranges were 50, right? We made them here. And the first element corresponds to the signal, the scores from our bigwig over this particular peak, this region. Okay, so from the beginning of the region, we have a run of 6, and then it will probably build up to be biggest in the middle, hopefully. And then, tails off at the end. And for our second peak, so this one here, we now have the scores within there running from the very beginning till the very end. So both of these are 50, although this one has slightly less runs. I guess there's less going on in this peak. Actually, that makes sense. We had less signal, smaller score. Okay, so that's really, really cool. We can take our RLE list object and we can now provide the G ranges here, and it's going to give us just the signal over those G ranges. Right? It's a bit of a pain. It doesn't give us a good name. Right? It'd be nice if it inherited this name, but we would rename it ourselves, I guess. So with that, we can now apply our sum statistic again. So remember we saw that we could use, I think max we used here, and this gave us the max per chromosome. Perhaps a little bit more usefully now, we can do sum, and we're going to get the RLE over our G ranges. So the scores over our G ranges here, and this is going to tell us that this first peak had more signal overall, a higher accumulation of signal, sum of signal, than our second peak. So already with our bigwigs, we've been able to start to get some summarization of signal over our peaks, over our regions, and start to do something kind of useful, get some scores. And we know that these do correlate with the score we're seeing here. I mean, this is probably a p-value or a minus log 10 p-value. But roughly we have double the score here than we do here, just by taking the simple tools we've learned to try and extract values over from our RLE over these G ranges. Okay, so we're going to be a little early for this session. So, and again, if you have Windows, you are going to struggle to export because Windows wasn't supported by UCSC. So when they wrote the tools in bigwig format, they didn't really think about Windows. There are solutions to this, but for these next parts, you're going to be frustrated if you're on Windows. So we may need to export our RLE list or RLE objects back to a bigwig. If we've done all this adding 10 or saying values less than 10 and now 0, we've cleaned up our RLE, our signal over the genomes. Now we want to extract that again. Right, we want to write that out, and we can look at that in IGV and get an idea of where our clear signal is. So similar that we couldn't write out a DNA string, we had to write out a DNA string set, because this is genomics and we want a value per chromosome. Here we're going to have to write out an RLE list. We can't just write out an RLE, and that's because it needs to associate this numeric values, this numeric RLE with a particular chromosome. But it's easy to do. We just do RLE list. We give it the name here, chromosome 1. To give it the numeric RLE we had stored in chromosome 1 underscore RLE. And then this is our RLE list here. We can now export that using this export.bw. This is a function from within the R track layer package. Give it the RLE list, tell it the connection we want to write to, and you will generate this .bw. Okay. In some cases, and this is something we're going to have to learn to deal with in any genomics data, really, especially if we're doing it in R, because R wants to read all the data into your memory in your local session. So in this case, we don't want to import a whole bigwig necessarily into memory. If I just want to look at 4 or 5 regions and get summary statistics over that, why read in the whole file? Bigwig has this index, right? We were looking at why it's so good at the beginning. It has this index built in, this self-describing format that bigwig is. So we should be able to just look for particular locations and extract just the signal in there. Okay, prior to having to read this in. So we can do this by taking advantage of this selection parameter inside the import.bw function, and also making use of this bigwig selection function. So if I just stop share for a second, I'll reshare my R. No, I don't want to leave meeting. That was the wrong button. So if I do export, so we had earlier on import.bw, and I think I said I would. Is that right? You know, we have different selections here, like as, and by default it's G-ranges. I know it's default because it tells me here that the default is G-ranges. But we had this option of hourly list. We did have this option of numeric list, which is very similar. But now we want to take advantage of something else here, which is this selection and this bigwig selection tool. Oh, and look here, it tells us these functions do not work on Windows. Frustrating, I promise you we are working on that too, to try and support Windows versions. Okay. If I wanted to, I could look a little bit more at bigwig selection. It looks kind of promising. We can just give it sets of ranges we want to retrieve back from our bigwig. So in the help here, it's really telling us everything we need. If I leave here, go back to our course. Right, so we're going to take advantage of just some additional parts of the import BW, and you're going to see something like bigwig selection for BAM files too. So what we're going to try and do is just import the bigwig or the signal from the bigwig over a set of here MIC peaks. We're going to do that by, as the function description said, passing our G-ranges to the selection parameter within bigwig selection. First, we need some peaks. We should already have these loaded. These are our new MIC peaks. Right, so this is our G-ranges object. So then we can create from our G-ranges object what is called a bigwig selection object using this bigwig selection function. So we just do bigwig selection. I give it my G-ranges, which these are the regions where I want to extract signal from the file and now when I do import DBW, I'm now going to specify our bigwig we want to import. I'm going to tell it I want it to be an hourly list, but really importantly, I'm going to give it this additional selection. And now when I read in this data, it's going to only read in the information from these peaks, which I actually asked for. It's still going to give me values for the other chromosomes, but it means I've only got signal, can only possibly extract signal from these particular peaks. Right, so this is going to save you a lot of memory and a lot of time, because it takes a while to read this in, if you're working on Mac and Linux when you're importing bigwigs. Great. So that's the end of this particular session. I have some exercises to do here. And if we can look, I think Matt had a poll maybe he wanted to do, I'm not sure. But I have some exercises here where we can start to do some manipulation of bigwigs. Again, if you're on Windows, you're not going to be able to do most of these exercises. Feel free to kind of look at the answers as well as you work through. But actually, I really like this exercise, starting to show you that you can take your bigwig and actually, although we will show you better ways of doing this, you can start to make ggplots of your signal, real genomic signal, over your particular region. So you can really customize what your graphics and what your plots will look like. Okay, and we show you a little bit more about manipulation in IGB and also using this to kind of summarize signal over peaks. Cool. So I think this will take, thanks, Matt. This will take a little bit longer, these exercises. So I'm going to give you until 1:45 maybe, and then we can meet and just run through them for 15 minutes at that point. So I was just going to quickly look at these exercises. I know perhaps we're in a break. So let me share my screen. That's a good start. So those are the exercises. Let's skip to the solutions. Anyway, so first thing we need to do is get hold of this file. Hopefully we've seen this now. at the beginning. You should have just Googled this, go to the ENCODE portal, takes you straight to this data set we're going to use throughout the course, and we can just download our Signal Bigwig there. Okay, we have a direct link as well. We're going to load some packages. So we load the RTrack layer package. Like I said, you don't need to load the genomic ranges once you've loaded this. But in this case, we've done this here anyway. It's just that our track layer depends on genomic ranges, so it's always going to load it. Okay, read the signal, the Bigwig signal from the region here as an RLE list. So actually I can, oh, really? Fantastic. Maybe maybe the newer versions are starting to accommodate bigwigs. That would be fantastic. Thank you so much, Jean, for letting me know. So anyway, fantastic. So what we can do here, and I just want to demonstrate really how fast this is because it's incredible. From a full-size bigwig, our studio. Yeah. From a full-size bigwig, we can really import just the data we want. So we can load the RTrack layer package. We create this region which we were particularly interested in right here. We have our full-size bigwig, but I'm now going to provide a selection object. Okay, so this will now be a bigwig selection. And it's telling us I want the ranges. It's actually saying I want the score column. So now if I read this in, it should be fairly instantaneous. There you go. Fantastic. All right, chromosome 1. Stop share. Okay, so we can read that in very fast and get our RLE. Find the maximum and minimum of value of bigwig signal in that region. Okay, I don't think I actually do the minimum here, but effectively we can either subset down to that particular chromosome, and we could actually go to that very specific region we selected here by just doing our standard subsetting. Okay, or we could do the same here where we can actually, because we've only imported signal from here, we could actually just do the max of this and subset it down to just that chromosome. So I think if I'm going to share my whole desktop because it makes my life a lot easier. Maybe not immediately easier. So then bigwig selection, we can just get that one particular chromosome, right? And then I could subset to just the region of interest. And then I could get the max of that. If I did just max on the whole bigwig thing, it's going to give me a chromosome score for every chromosome, right? And this was kind of cool for us originally. I just need to subset down to the chromosome I'm interested in, and that should be the same score because we only imported signal over that region. So then produce an area plot, okay, of the signal over the transcriptional start site plus or minus 500 base pairs of the gene start for this particular gene. Okay, so then you would go into ggplot, IGV, maybe get the actual position of that TSS. I'm just going to minus 500. Right, so this is going to give me the start position minus 500 and obviously plus 500. And if I use this function seek, which we saw in the very early lectures, it's going to give me a sequence of numbers from this position, this number here, to this number, just going up in values of 1. I can also extract from my bigwig of chromosome 1, then I can extract all the values for those positions. Okay, so I'm going to use these as an index on my numeric RLE, and I will get just the scores over these base pairs I'm specifying. I want to turn that into a data frame because I'm going to use ggplot. ggplot likes data frames. You can then add the position, right, so that on our bottom of our ggplot, it's got actually the genomic position rather than just running from 1 to the end. And then load ggplot. Maybe it's already loaded. And then I can pass in this data frame here where I have value and position. I will do position along the x-axis, value along the y. I'm going to do a geom area plot, right? So it's going to fill in all the area under the line. Do theme minimal, and I'm going to add some xlab, ylab. Going to change the theme, right? And this is just a nice example of changing the angle of the text on my axis. If I put that all together, I should get something like this. Okay, so great. So I can actually have the signal per base pair over my region, and I can then plot this in ggplot. We're going to show you later on in the courses how you can make these plots in really beautiful ways using gviz. Very similar looking, very ggplot style of plotting genomic regions. But if you wanted to do it yourself, you can do it. Apply a log2 transformation. So this is our bigwig without the log2 transformation. I think they saved this to a new bigwig just so we don't mess our old one. And then I apply the log2 transformation. And then 0 is going to become infinite. -2, let's just transform this first. But again, it's going to do this very quickly in a very efficient way. So once you've done all this and you've made your bigwigs, you can then export this bigwig back out to file right here by just doing export.bw. You give it log2.bigwig. This is what I'm going to write it to. I give it my modified RLE list. Just write them out. And in my present working directory, I should get my new bigwig somewhere. Log2.bigwig. Okay, read in the file and create a G ranges of all peaks on chromosome 1. That's kind of straightforward. Just load these again. Probably don't need to. I can read in this what is called an XLS. It has some where is it? Nick. CH12 peaks. Which one? This one. Yep. Maybe that's a little big. Oh, okay. So actually, it doesn't have anything at the top. Did I load the right one? Ah, great. So I'm not sure if you can, hopefully you can see my screen, but the first few lines had these hash at the beginning. What we want to do is avoid reading in the hash. We just want to read in the actual peak names, peak information. So what we're going to do then, what we're going to do then is say comment char is hash, and it's going to ignore any lines which started with a hash. Tab separated, read that in, and then we did this in our last session as well, our last exercises. We created G ranges from the various components. And then we just subset that to only the G ranges where the names, the seq names, the chromosome. So using these G ranges, import. So again, we saw this in the courses, in the actual lecture of this. We need to create a bigwig selection from our G ranges, and this is going to allow us to import just the signal which fell over these peaks. And now if I do that, I now should have an RLE list. Great, and I've just imported, right, so this signal here only includes any signal which came from within these peaks. This will save us a lot of memory. Import the gene positions for mm10 genepols.igv as a G ranges, filter to genes on chromosome 1, identify peaks overlapping the gene's promoter, here defined as a region ranging from 2000 base pairs upstream to the transcriptional start site, and those not overlapping. So the first thing we need to do is to read in this data, and we get just a standard data frame, but we have all the information we need: gene name, chromosome, start, end, strand. So I can turn that into a G ranges pretty easily using providing the information as we need in the constructor. And then I have my gene chromosome, start, end, strand. I haven't bothered keeping the names yet, but now I can add them in here. I should have my names here. Okay, we're going to do this resizing. So I'm going to resize to the start of the gene They're stranded, so it's always going to find the correct start dependent on the strand. If it's on the negative, it will be on the right. So we do that, and we have our TSS positions, and then I just want to extend them up so that they work from the end and go, because this is just one base pair now, and go upstream. Okay, and then we have our positions there. On the negative, it goes there and then goes to the right. And the positive starts there and goes to the left. And then we can just overlap with these promoter regions and just find the MIC peaks, which overlaps with the promoter peaks, promoter regions. And this then gives us two sets of peaks. Promoter peaks here, these overlapping these regions, and then those not overlapping those regions specified by this exclamation mark you see here. So create a violin plot of the sum of bigwig signal within peaks at promoters and those not at promoters using ggplot2. Okay, so we need to first extract the signal over these peaks. So we have our G ranges here, promoter peaks. We have our bigwig RLE list. So then we did this in the course. If I want to turn this RLE list now into an RLE list of where every element now is the peaks, right? I just need to supply my G ranges of peaks within this square brackets for my RLE list. And then I've now got 188 plus them, so 193 numeric RLEs, and these contain the signal working across our peaks. Okay, actually, I don't really care about how the signal looks. I just want to get the sums, so I can just summarize up the signal anywhere within the peaks and get the. I got sum. I'm calling them peaks max for some reason. But there, and I'm going to do that separately for the non-promoter peaks. Okay, so I've got two sets. Okay, I'm now going to put them together into a data frame. So I'm going to create a data frame with these scores here, and then just a label to say they were promoter. I'll create another data frame with the non-promoter ones, and then we'll use rbind to put these two data frames in. So one data frame's the scores for every non-promoter peak, and the scores, some scores for every promoter peak. We're going to do a violin plot. So we can pass this to ggplot2. There's a data frame, the X. So working across is going to be this column. So it's going to break it into two groups, promoter, non-promoter. The Y, how high it is, will be the sum. And then we'll do a color, not just the outside, we'll do fill, and we'll say it needs to be whether or not you're promoter or not promoter. Give it the violin that we want a geom violin. I'm going to scale this. Tends to be with counts, we want to log scale it. Often log 2, but here I'm doing log 10. I'm going to add some custom palette here. And there we have our violin plots of promoter and non-promoter peaks, the average signal. So I think the last thing we were going to do is really just filter down bed file of TSS peaks whose sum of chip signal is twofold greater than the median of all peaks sum signals. So we'll get all our RE here. And we have here our coverage in our promoters. We have here our coverage in our other peaks. Promote max coverage. Let me find out where that happened. Oh, I think we've got this a little bit kind of muddled up across the two here. So we can have to skip down a bit. So again, let's read this again. Export a bed file of TSS peaks whose sum of chip signal is twofold greater than the median of all peaks. Okay, so we have our G ranges here. We can actually get just the signal over our G ranges. Oh, no such file. Oh, right, this is actually a different bit. Here we go. So we can import our bigwigs over our previous G ranges peaks here. We've removed an exercise at some point. So if I wanted to get just the promoter peaks from this, I can get just the coverage over these peaks. I can get the sum, so I can get the total sum of signal in these peaks. I think I actually wanted the mean. That's the sum. What I might want to do then is I might want to get the median or median of that sum. Okay. And then I could take my promoter sum peaks, which are greater than the median. Okay. And then if we wanted to export these to an actual file, we'd do export.bed, and we get it promoter peaks. So these are promoter peaks where the sum of signal is greater than the median sum of all the signal across the peaks. And then we'll just write them out to a file, but it's not file, it's con, and peaks above cutoff. Great, so I think those are all the exercises. I'm going to go back and tidy up. I see that we've actually have an exercise where this has all been commented out. So I'm going to go back and see what happened there. So I think this exercise doesn't actually relate. The solution doesn't relate, but we have the solution here, so I can update the exercise. Okay, so that's the exercises for this particular genomic scores. Thank you, Jean-Nicolas, for giving us this information about Windows 10. That's actually fascinating. I'm going to investigate the change which must have happened there, but maybe they caught up and started using a slightly better library. But I will see the rest of you back at 2:30 when we can go through the last session.